We saw a laser has 4 properties in which we learnt about intensity, monochromaticity and directionality. Now we shall take a look at the 4th and final property, which is coherence. So when do I say two sources of light are coherent? Not necessarily light, anything. When do I say two sound waves, light waves, or two waves of electromagnetic radiation or whatever, when do I say two waves are coherent? They need to have the same frequency and same or constant phase difference. So these are the necessary conditions for two waves to be coherent: same frequency and same or constant phase difference. Now we will first try to understand these two cases. What if the phase difference is not constant, and what if the amplitudes are not equal? Because I have not mentioned amplitude here as one of the necessary conditions for coherence. So we will see why phase difference is important, because same frequency is intuitively we know when we say two waves are coherent, we mean that we can superimpose them smoothly without any interference, without any destructive interference. That is what coherence means. And for that same frequency, we more or less intuitively we know that is when the waves have a similar shape on graph, and that is when smooth interference happens. But why is same or constant phase difference an important condition, and is it fine if the amplitudes are not equal? We will first try to understand these two, and then we will study about a quantitative measure for coherence and lasers in relation to coherence and all that. So we first begin by seeing what happens if the phase difference is not constant. So let's say these are two waves. This is one wave and this is another wave, and they have the same frequency, but the phase difference is not the phases are not same. First of all, there is a phase difference, and more importantly, the phase difference is not constant. So here at the starting point, this wave is at 0 and this wave is, let's say it is at minus pi by 2. At this point both are at the same place, but when you see this location, this wave is at 0, this one is at minus pi by 2. So the phase difference at this point was pi by 2, here the phase difference is 0, again here it becomes pi by 2. At this point this wave is at plus pi by 2, this one is at 0, again there is a pi by 2 difference. Here at this point in time, this wave is at plus pi by 2, this wave is at minus pi by 2, so you have a phase difference of pi. So there is not only a phase difference, but the difference does not remain constant. So at one point the difference in phase is pi by 2, at one point it is 0, at one point it is pi, and so on. So of course this is a very rough diagrammatic representation. It's not to scale, there's nothing mathematical about it, but you get the idea. So what happens when we try to superimpose two such waves is they cause interference. So why are we talking about superimposing waves in the first place? Because in repeated amplification we saw that there are waves which fall on the mirror with different phases. So by repeated amplification we try to minimize the phase difference, and then ultimately we are going to superimpose all those waves or photons together to produce light. And we also know that laser light is highly intense, so I want maximum intensity. But if I take two waves like this, when I superimpose them, at some locations the waves are just going to cancel each other out. For example, here I have a plus pi by 2 phase difference and this one is minus pi by 2. So at this point both the photons, the waves associated with both the photons, they just cancel each other out, and I have zero intensity. So at that point I will find a dark spot instead of light being emitted, and we cannot afford that, right? Which is why a phase difference is allowed, but it has to be constant. The phase difference cannot keep changing. So that's what we saw: same frequency of course, and same or constant phase difference. That is part 1. Now we try to answer another question: what if the amplitudes are not equal? Is it necessary for the amplitudes also to be equal in order to call two sources as coherent, or is different amplitudes fine? So again we'll try to understand that with the help of an example. These are again two waves. They have the same frequency and you can see the same phase difference. At corresponding locations their positions are the same. So the phase difference is the phase difference is either 0 or constant. The only difference between the two waves being their amplitude. So let's say this has an amplitude of pi by 2, for example. This one might be pi or something. So frequency is the same, phase difference is constant, but amplitudes are different. So when I try to superimpose these waves, what happens is I get a wave like this, where the peak spots or the bright spots are very bright. There's something called a crest and trough of a wave, if you know. So trough is like the bottommost point and crest is the uppermost. So at the crest, where maximum proactive interference takes place, you get a spot with maximum brightness, maximum intensity, which is perfectly what we need for a laser. At the trough, where the destructive interference takes place, because this amplitude is less compared to this, you do not find zero brightness, you don't find a complete cancel out each other type of interference. There is some non-zero value, so you find some little bit of brightness. So these orange spots indicate that light, a photon or a light wave is there, but it is not as intense as these red spots. Meaning, so essentially what I am trying to say is, when you combine two waves whose only difference is amplitude, they interfere due to superimposition. At the crest, you will find spots of maximum brightness in the interference pattern. At the trough, it will not be a completely dark spot. Instead, you will find a less brighter, mildly bright spot. And that is perfectly fine, because we are not doing something like a Young's double slit experiment here, where you need a perfect bright spot, dark spot, bright spot, dark spot. Our intention itself is to produce light of maximum intensity. So if we actually have a few milder spots instead of complete darkness in the middle, it is to our added benefit. So to have unequal amplitudes is perfectly okay. So what did we just understand from this video? Coherence is one of the properties of a laser. We haven't yet related it to lasers and learned, which we will be doing. But the point is, to say that two waves are coherent, A, their frequency has to be the same. B, either they should have the same phase, meaning phase difference should be 0, or if they have a phase difference, it should be constant. Within the wave, the phase difference cannot change. It cannot be 0 at one point, pi by 2 at another, pi at another, and so on. Constant phase difference. C, the amplitude may or may not be equal, does not make a difference. So these are the necessary conditions for coherence. We will now see coherence with respect to lasers.